Hi, I'm Amir.
I'm Jim. In this video, we're gonna talk about the Euler's method.
So what is Euler's method?
Euler's method, which is a numerical method that we can use to approximate the solution to differential equation.
So what exactly does that mean?
Well, just like it sounds, it's a method that we can use to approximate or estimate the solution to differential equation, in particular, the differential equation initial value problem.
So what does it imply about when we use Euler's method?
Well, it implies that we use it when we can find an exact solution. It also implies that we can use another method to find an exact solution.
So the interesting part is that the way we study differential equation makes us think that most differential equations come in one of these forms. They are almost all separable differential equation, exact differential equation, or linear differential equation.
Well, in fact, exactly the opposite is true. Very few differential equations fit one of these exact formats: separable, exact, and linear differential equation. But most of differential equations don't fit any of this format at all and can be solved using the method that we normally use to solve this kind of differential equations.
If we're given a differential equation and it's not separable, not in the form of exact, or not in the form of linear differential equation, then how do we go about finding a solution to that particular differential equation?
Well, that's where a numerical method can come in and help us find an approximate solution or estimate of the exact solution. And Euler's method is the easiest, most popular numerical method to use to find an approximation for the solution of differential equation.
Commercial break!
We'll be doing 3 experiments regarding something that is very important to us. So what do you think is that certain something that is very important to us?
The air,
It's like sweet down.
water,
So yes, we'll be doing experiments relating to water. So first, the first experiment, we need something, a flat surface, a glass, water, rubber band, and mesh. So what happens if I pour water inside this glass, and when I tilt it, what will happen? So will it spill or not?
feel.
So yes, it will spill. So any volunteers? So sir, what's your name? So sir, Amir, can you please sit there? So what happens?
Go, go, go.
This glass of water, cover it with a flat surface and put it above his head. So what do you think will happen? Will it spill or not? No.
Go feel.
So let's see. Did it spill or not?
Not.
So what happened? So as you can see, when I tilted it, the water flowed out. So what happened is water has high surface tension. So sir, thank you po. So water has high surface tension. So what happens is when I put water inside and put it on a flat surface, the water molecules help each other to form a tight bond between each other and fill the spaces between the holes. So when that happens, water did not flow out, and as you can see, Sir Amir did not get wet. So,
A few moments later.
In this part, I will show you the Euler's formula and the proof without Taylor series. So, we let f of theta is equal to e raised to negative I theta cosine theta plus I sine theta. So from this formula, we derive this into derivation of theta, and the derivation of I theta is negative I e raised to I negative theta cosine theta plus I sine theta. So we derive this one, and then for the next part we differentiate this one. So e is I theta. So derivation of the cosine is negative sine theta, and the sine is plus I cosine theta. And the next is we distribute the I inside this equation. So e raised to I theta. So negative I times cosine is negative I cosine theta plus, so negative I plus I sine is cancel, so I sine theta plus, and then copy e theta sine theta plus I cosine theta. And then after this, we factor out the same. Okay, e negative I theta, so it's factor, and then bring down sine theta, and then negative sine theta plus I cosine theta. So we evaluate one. So I sine plus I cosine theta plus I cosine is cancel. So sine theta minus, so cancel then. So e raised to I theta times 0. So our derivative of theta is equal to 0. So we know if the derivative of theta is equal to 0, then the original function is constant. So we know that f of theta is equal to k, and we use this for all the theta. Then from this, we substitute the value of theta in this equation. So f of 0 is equal to e negative I times 0 cosine 0 plus I sine 0. Okay, so we get e raised to I times 0, so e raised to 0 is equal to 1, and then cosine 0 is 1 plus sine 0 is 0 times I, so 0 I. So we get the value of k 1, so this is equal to k, so our k is equal to 1. So from this we get the value of k, and then yes, we get the value of k is equal to 1. So we know that f of theta is equal to k, so f of theta is equal to 1. So we substitute the value of theta, so we know that f of theta is e raised to negative I cosine plus I sine theta. So e raised to I theta is cosine theta plus I sine theta is equal to 1. So we multiply both sides by 1 over e raised to negative I theta. So we get the cosine theta plus I sine theta is equal to e I theta. So from here, we get the formula same as here. So, and we get the Euler's identity from this formula. So, from this formula, we let theta is equal to pi. So, cosine pi plus I sine pi is equal to e I pi. So we know that cosine pi is negative 1 plus I sine pi is 0 equal to e I pi. So we transpose the negative 1. So we get e I pi plus 1 is equal to 0. So what's amazing in this Euler's identity is that they link together in one simple relationship and four completely different concepts in mathematics. So the E is the Euler's number. Euler's number. The I and the pi, the cosine and sine, and the I for the imaginary numbers. And that's the most beautiful equation in mathematics. So this is the application of Euler's method in differential equation. How does it work? I will show you this formula using this graph. For example, you have a solution curve like this, and you have an initial point right here, which is the x sub 0, y sub 0. So from that point, we draw a tangent line. Okay, and let's say this point is your final value. So which is the x sub 1 and y sub 1. So from these 2 points, we create a right triangle. Yes, and as you can see, we have a distance from x sub 0 from x sub 1, which is called our step size or the h. And we need to get the value or the distance from y sub 0 to y sub 1. So we know that gradient is equal to rise over run. Say x sub 0, x sub 1 is equal to x sub 0 plus the h, and our y sub 1 is equal to y sub 0. We need to add from here. Okay, our rise is the unknown and our run is the h. We know that our gradient is x0, y sub 0 here, and our rise is unknown over the h. So we cross multiply the h times x0, y0 with unknown. So we add this formula. We add this formula to y sub 0. So plus h sub 0, y sub 0. So it's the same as this one. We have another way to get this formula. Like I said, our rise over run, the gradient. Our gradient is f sub 0, y sub 0 is equal to, our rise here is y sub 0 minus y sub 1, or y sub 1 minus y sub 0 over x sub 1 minus x sub 0. We cross multiply. So x sub 1 minus x sub 0 times f 0 y sub 0 is equal to y1 minus y0. we transpose the negative y sub 0 to the left side. So we know that x of 1 minus x of is h. So y sub 0 plus h, and then times f 0 sub 0 is equal to y1. So it's almost the same. So that's how we get the formula using this graph.
Thanks to Sir Leonard Euler, who introduced to us the nature in solving such differential equation.